Okay, so this question is more about coordinate geometry, and in particular how gradients of lines relate to the tangent function. Okay, so in this question we have two lines, L1 and L2, with different gradients and different y-intercepts, and we want to prove this formula for um, for the acute angle between them. Okay, so we want to prove this, where m1 and m2 are the respective gradients of the lines, where theta is the acute angle between L1 and L2, okay, as labeled here. This is a question. So there are a couple of things given this question that I think you should notice immediately. Um, and firstly, that's the form of the formula that we're looking for. And what should immediately spring to mind is that this looks remarkably like the um, tan argument subtraction formula, which is this. You should know this, but just for a reminder, this is tan A minus tan B over 1 plus tan A tan B. And this right hand side looks remarkably similar, right? Where M1 is tan A and M2 is tan B. And so that already gives you massive clues to this question. But let's have a more detailed look. So if we zoom in on, well, if we have our two lines like this, pressing here, and we're interested in the angle they make with the x-axis. So if we draw a line through here, so let's label some angles. This here is theta. This one is, we'll call theta 1. Yeah, because that's the one for L1. So this is theta 1. And just to be consistent, we want to measure from the positive x-axis. And so we'll call the angle to the other one theta 2. Okay, I didn't go down because then we've got angles going in different directions. You could get it to work that way, but I think maybe this is clearer. So now looking at this diagram, we can see that, well, theta 2 minus theta 1 is equal to, well, if we take theta 2 and minus theta 1, then that's everything outside of theta, right? If you think where this line is going to be, if those two cancel each other out, right? So, in fact, maybe simpler to write theta 2 minus theta 1 plus theta is 360 or 2 pi, we'll use radians, is 2 pi radians. Okay, I think you can see that from the diagram. So in particular, if we recall what we're aiming for, in particular, we're interested in tan of theta, right? This is the formula we're trying to prove. So in particular, theta is 2 pi plus theta 1 minus theta 2, and as tan is pi periodic, i.e. tan of theta plus pi is tan theta for all theta, we have that tan of theta is equal to tan of theta 1 minus theta 2. And this, from above, is exactly what we were hoping for, right? We've got a difference of arguments, so we can expand this and get something which looks like this. So now there's one last thing we need to do is, well, what is theta 1 with reference to our initial equation? Well, theta 1 is the angle the L1 line makes with the x-axis. And that relates very strongly to the gradient. In particular, the gradient is like the rise over run, right? M1 gradient is the rise over the run. So if we go up by m and across by 1, this is the gradient of m. Okay, But then what's this angle here, theta? In fact, I'll draw this out. I'll draw this out much better here. So if we have, for every one that we go across, we go up by m, right? This is our line. Then this angle here, theta, by our basic trigonometry, because this is a right angle, we have that tan theta equals the opposite divided by the adjacent, which is m over 1, which is m. So tan of theta 1 is m1, and tan of theta 2 is m2. So now, substituting into this formula, I'll write everything out again. So we have tan theta is tan theta 1 minus theta 2, and tan theta 1 is m1, tan theta 2 is m2, so call this star, expanding star gives, as we did before, tan theta is theta 1 minus theta 2, tan theta 1 minus tan theta 2 over 1 plus tan theta 1, tan theta 2, but we can substitute in the values because we know what tan theta 1 and tan theta 2 are, and this is m1 minus m2 over 1 plus m1, m2, and this is exactly what we were aiming for over here.